Hi. So, in the previous video, we learned how to calculate a particular integral. So we know how to find the equilibrium solution. The other part of the time path, so the full solution, complete solution, is a complementary function, which is showing to us what happens when y is out of the equilibrium. Now, I hope you remember from our classes about first order differential equations that in order to find the complementary function, what we need to do is to solve the reduced solution or a homogeneous equation. What do we mean by homogeneous equation? It's the equation that on the right hand side has got just 0. So in our case, this is going to be y plus a 1 y prime plus a 2 y equals to 0. But look, we do not need to start from scratch. We already know what was the solution in the case of first order differential equation. I hope you remember the complementary function there was given by a times e to the power negative a t. Right? So, how about now we're gonna use this information and try to do something similar. But look, our tried solution is going to be in a little bit more general form. Let's try that y is equal to a e to the power r t, where our r is like corresponding to this negative a, but for reasons that will become obvious, we don't want to no longer use a, right? Plus we've got a1 and a2 over here. This might be confusing. Let's switch to r. Okay, now that we know that this is our trial solution, the next thing we should do is, of course, if we know what is y, is find to y prime and y base. Right? Here I just use the exponential rule of differentiation, so I put r up front. Right? Because derivative of the exponential function, right, is derivative of what we have over here, of course, with base e. We just differentiate this with respect to t, we put it up front. Okay. So, now we are ready to calculate y base. But look, now we differentiate this and the same happens. So, we differentiate just this part and r goes up front. So, we get r squared a e r t. Okay. So, now that we've calculated it, why just not to substitute this into the equation? Okay, so let's do it. So we've got that this is r squared times a e r t plus n1 r a e r t plus a2 a e r t equals to 0. Okay, and look, we clearly see that all these expressions share the same component, AERT. So why not just take it out of the parentheses, right? So we get that this is AERT times r squared plus a1r plus a2, and that's it, equals to 0. And now let's think about it for a second. Look, we clearly see here that e to the power rt doesn't matter what R is, what T is, it can never be 0. Right? We will always get out of this expression a positive number. It can be very, very small, but only in infinity, with t approaching infinity, it will go to 0, right? So, what we get out of this is that this cannot be equal to 0, right? And how about A? If A would be 0, again our considerations wouldn't matter much, right? This would be very bad case. Plus, not interesting, we would still be in equilibrium, right? Because here are our deviations from equilibrium. They are measured by A, right? So, we also exclude this possibility. But if this is true, then our equation reduces to r squared plus a1r plus a2 equals to 0. And look, this equation that you see over here is called characteristic equation. Characteristic equation. Okay, so for this differential equation, homogeneous differential equation, this is its characteristic equation. But of course, look, if here we would have 7, it wouldn't change anything. We would still have the same characteristic equation. So it works. It works here even if we have not just 0. Okay. Now, let's think about this characteristic equation. Have we ever seen it in our lives? Probably not in this particular form, but I'm 100% sure that we've all seen it in this form, right? This equation is simply associated with quadratic formula. Look, what is the difference? A is simply 1, B is A1, C is A2, and of course X is R. So we can solve it. Okay, so what are the solutions? Well, I hope you remember that the solutions depend on value of delta. But what was this delta? Delta was b squared minus 4ac, right? Depending on the value of this particular expression, we will have different solutions. But those solutions were x1 and x2. They are given by negative b plus minus square root of delta. But let's write the square root of delta in this form. B squared minus 4ac, and this whole thing divided by 2. Okay, but look, we of course don't want to solve this more general case. We are interested in our characteristic equation. So, but by using the correspondence between those two cases, we can easily write the solution to our equation. Okay, so our b is a1, right? So our solution will start with negative a1, then there will be plus minus, and our b is still a1, right? So we've got this must be a1 squared, and now minus 4. Our a is just 1, and our c is A2. So 4A2. And this whole thing divided by 2. And those two roots of this characteristic equation that you see over here are called characteristic roots. Okay, so that was pretty easy this far. Look, actually now we know how we can solve this. And look, if we're going to solve this, for R1 and R2, we will be able to fill those R1 and R2 over here. But this should immediately create some issues in your head with this. Yeah, but here we've got just one R. So why do we have two R's over here? Well, this is a quadratic formula, so we expect to have two solutions. But, however, we should remember that depending on the particular value of delta, we can have two solutions, one solution, or what you were taught before, zero solutions. However, at the beginning of the mathematics class, I told you that this is not necessarily true, because there are solutions also when we have negative number over here. They are called complex solutions. And this is something that we are going to tackle in the future. Actually, during the next class. But for now, let's concentrate on what we have. So look, we are getting very close to solving this problem. But before we move on, let's use one more thing you know very well, which are Viet theorems or Viet formulas. And those are saying that if I'm going to take R1 and I'm going to add to it R2, what am I going to get? Well, let's try it. Look, we know that R1 is negative A1 plus square root of A1 squared minus 4A2 over 2. Then I'm going to add to it negative A1 plus, minus, right? A1 squared minus 4A2 divided by 2. And look, what happens? Those two expressions would cancel each other out, right? So what I'm ending up in here is negative 2A1 over 2 or negative A1. So what we got is that the sum of the two roots, regardless of what case we're talking about, is always equal to negative A1. Now look, we can do the very same thing with the product of the two. Okay, and look, so now what I need to do is to multiply these two expressions by each other. And look, actually, when we multiply two fractions, right, we multiply numerators and denominators. So in the denominator, we will have 4. And look, here the case is that we take some A plus B, right? This is our A, minus A1 is A, and this is B. And we multiply it by A minus B, right? Which should give us A squared minus B squared. Let's apply it over here. So we get that this is negative A1 squared minus square root of A1 squared minus 4A2 squared. Okay, if we calculate it all out, we get that this is a1 squared minus, we just get rid of the root here, and a1 squared minus 4a2 divided by 4. And again, now those two cancel each other out. We end up with negative 4a2 divided by 4, or simply negative a negative a. We end up with negative a2. If I didn't make a mistake, did I make a? Where did I make a mistake? Oh, of course. I'm sorry, because it's minus and minus. Gives us plus. That was, of course, I saw that it shouldn't be like that. Yeah. So we've got just a2, right? Minus and minus gives us plus, right? So we get another relationship that R1 times R2. So the product of two characteristic roots must be equal to a2. Okay, those two results will be very, very important to us in the future. But for now, but for now we can forget about it. Just they are not like very necessary for our deliberations on how the complementary function works. But you will later see that using those two relationships is going to be extremely crucial if you want to do something in a very easy way. So if you don't want to have too much work. Okay. So now that we've covered this, let's go further with our main analysis. So we got this characteristic equation for this trial solution, and let's imagine that what we did is that we actually calculated R1 and R2. And look, this actually gives us two solutions. Y1 equal to, so A1 times e to the power R1t, and Y2 equal to A2 e to the power R2 t. Those two outcomes are the functions we were looking for, right? However, look at this situation. We've got two different solutions, and we've got two arbitrary constants. Doesn't make sense? Well, remember one thing. This is second order differential equation. So it means that we have second derivative in it. But if we have second derivative in it, doesn't this mean that we should have lost two arbitrary constants, right? Two constants in the process of differentiation? Well, it makes perfect sense. So this is why it's not only, I didn't put here or, I put and. We need to use both of these results at the same time. So, what does it tell us is that now we will have two sets of solutions, right? So we've got y1 prime, right? Plus a1, y1, I'm sorry, b1 prime, plus a2, y, and this is equal to 0, right? And this is 1. And the same we've got for y2. them up, right? What would we have here? We would have here y1 bis plus y2 bis plus a1 y1 prime plus y2 prime plus a2 times y1 plus y2. Okay, and look, this makes perfect sense. Everything checks out here. Because look, for example, derivative of a sum is equal to sum of two derivatives, right? So if I would differentiate this, is simply what I would get if I differentiate it twice, y with respect to time, right? What we see over here is what I would get if I differentiated y1 and y2 just once with respect to time. Okay, so look, going from here, we finally established what is going to be our complementary function. And the complementary function for this case yc is going to be equal to y1 plus y2. So it's going to be a sum of those two y's. Oh, sorry. However, this is not the end. As we said before, actually, the values of the roots and the number of the roots depends on delta. In our case, in this delta characteristic equation is simply a1 squared minus 4a2. And look, it can take different values. First of all, it can be positive. Second of all, it can be equal to 0. And third possibility is that it is negative. However, if it is negative, situation complicates, and in high school, you were never touching this subject, right? This is where you stop. We're going to do it next time. For now, let's just concentrate on case number 1 and case number 2. So, look, again, we are having differential equation, a differential equation y is plus a1y prime plus a2y equals to, let me just look at the example. Oh, okay, we're going to start with the general case like equal to some b, right? We know, because we know that now all we have to do is to use our solution that we have obtained, and we can calculate the complementary function on any equation. And look, let's just say that we've got this equation. And what happened? It happened that we've got case number 1. Case number 1 is the one that we're going to call real distinct real roots. Okay, what does it mean, distinct real roots? There are going to be real numbers, and there are going to be two different numbers. When will we have a situation like that? Of course, when delta is bigger than 0, which means that the expression you see over here, a1 squared minus 4a2, needs to be bigger than 0, which also says that a1 squared needs to be bigger than 4a2. So this case is actually the simplest, because all we need to do in this is apply what we already found out. Okay, so in this particular case, we will have what? Complementary function is going to be y1 plus y2, just as we said, and this is going to be equal to a1 e to the power r1t plus a2 e to the power r2t. So now that we've got this, all we have to do is to practice it a little bit, right? So let's start an example. Okay, so our example is going to be like this. Let's just say that we've got a differential equation in the form y plus y prime minus 2y equals to negative 10. Okay, let's start with particular integral, so with the equilibrium solution. Here, because a2 is different than 0, we know that particular integral given by b over a2 is equal to negative 10 over negative 2, which is equal to 5. So particular integral is stationary equilibrium, it's constant equilibrium at 5. Okay, now the second thing we need to do is to find complementary function. Okay, look, we do not need to repeat the process that we did because we already know the formulas. Let's just first check if a1 squared, which in our case is 1 squared, which is 1, is actually bigger than 4a2, which in our case is 4 times negative 2, which is negative 8. And this is clearly the case. 1 is bigger than negative 8. So we've got this case, which means we've got distinct real roots. Okay, so what are those two distinct real roots? This is not that complicated. We just use the formula. R1, R2 is negative A1 plus minus A1 squared minus 4A minus 4A2 over 2. Right? So we've got this is negative 1 plus minus square root of 1 minus negative 8, which is 9 over 2. So we've got negative 1 plus minus 3 over 2, which gives us 2 over 2, which is 1, and negative 4 over 2, which is negative 2. And look, right away, we are ready to write down the complementary function. It's given by a1 times e to the power r, which is r1, which is equal to 1, times t, which is t, plus a2 times e to the power r2, which is negative 2, times t. And this is our complementary function. So, finally, we are ready to draw, to put down the time path, so our general solution. Our general solution is composed out of complementary function and particular integral. And so it is given by a1 e to the power of t plus a2 e to the power negative 2t plus, I believe that was 5. Okay, so as you see, finding the solution in this case is not that complicated. But let's just go one step further. What do I mean by one step further? Let's find a specific solution. Because for now we've got just general solution. In order to get this one, we need to have some initial conditions. And remember, when we were talking about first order differential equation, we just get one initial condition, right? Because we had only one arbitrary constant to definitize. However, now that we've got two, we need to have two initial conditions. And let's just say that in our case, those two initial conditions are going to be y of 0 equals to 12 and y prime of 0 is equal to negative 2. Okay, so first thing we should do is to calculate y of 0, right? So we take our general solution and we substitute 0. We get that this is a1 e to the power of 0 plus a2 e to the power negative 2 times 0 plus 5, right? So this is a1 plus a2, right? Because this is 1, this is 1, plus 5. And look, we know from here that this must be equal to 12. Okay, so now, we're gonna use, we need to use second initial condition, but before we do so, we need to calculate the first derivative. So we take the time path and we calculate its first derivative. So we get that we differentiate this. Again, we need to differentiate just the exponent. It's 1, so it's nothing changes. a1 et. Then we differentiate again just by differentiating this. So minus negative 2 goes up front. So we got 2 times a2 e to the power negative 2t. And after differentiating 5, we'll just get 0, right? So, and this of course needs to be, and that's it. Okay, for now this is it, right? And the second thing is, in order to get a second initial condition, we utilize second initial condition. We need to substitute 0 in the first derivative. And so we get this is just a1, right? Again, we substitute 0. Minus 2, a2, again, we would get 0. And we get that this is equal to negative 2. So basically, over here and over here, we've got a system of two simultaneous equations, right? We can simplify this one by subtracting 7 from both sides, and 5 from both sides, and we will get 7 over here. So look, the two equations we've got are a1 plus a2 equal to 7, and a1 minus 2a2 equals to negative 2. And let me just put this in matrix notation. So we've got 1, 1, 1, negative 2, a1, a2, 7, negative 2. Okay, first we should check if we've got solutions. So we calculate determinant A, and we've got that this is negative 2 minus 1, it's negative 3, it's different than 0. We know that the solutions exist. Okay, so let's denote we've got solutions. And what do we do next? No, well, then we just need to solve the system. Let's do it using Cramer's rule. And so we calculate first, I don't know how to call it, A1. Well, probably this is going to be the best way to do it. And what do we get here? We get that this is 7, negative 2, 1, negative 2, right? So this is negative 14 plus negative 14 plus 2, which is simply negative 12. And we've got this second one, A2, which gives us 1, 1, 7, negative 2. And this is negative 2. Negative 2 minus 7 is negative 9. So we get that A1, which is equal to this determinant divided by main determinant. So this is negative 12 over negative 3 gives us 4. And A2 is negative 9 over negative 3, which gives us simply 3. Okay, and I know that this was rather long, but once you get used to it, you can do it extremely fast. However, our final solution to this problem tells us that y of t is equal. Now we substitute 4 for a1, so we've got 4e to the power of t, 4e to the power of t, we've got plus 3 plus 3e to the power negative 2t plus 5. Okay, so this is the solution to the case number 1. So now what we should probably do is to start with case number 2.